What if you had a superpower? What if you could see the precise individual arrangement of atoms in any material you wanted? Not in a computer simulation or a textbook diagram, but right in front of you here in reality. Imagine being able to map the atomic architecture of a new medicine to fight a deadly disease, or analyzing the crystal structure of a new alloy for a spaceship destined for Mars. This isn't science fiction, it's happening right now in a field of science that is building the future. It's a power that has unlocked the secrets of life itself and continues to show us what we can create. But how? How on earth can we see something a million times smaller than a single human hair? The answer isn't a better microscope, not exactly anyway. It's a mysterious form of light discovered by accident over a century ago, and a stroke of genius that turned matter into a lens. This is the story of how scientists use X-rays to see the impossible. Hello and welcome to the Chemist's Codex. My name is Peter, and I like to find stories and the things that catch my interest because I believe those stories can teach us more about ourselves. To get a grip on this superpower, we first need to talk about what seeing actually is. When you look at an object, your eyes are just detecting photons, particles of visible light, that have bounced off it. Your brain does the rest. But here's the catch. For this to work, the waves of light have to be smaller than the object they're bouncing off. Try thinking of it like this. You're trying to feel the shape of a tiny pebble with your bare hand. Easy, right? Now try to figure out the shape of that same pebble using a giant beach ball. You can't, at least not very well. The beach ball is just too big and clumsy to notice the pebble's fine details. It would just roll right over it. That's the exact problem scientists face with atoms. Atoms are ridiculously small on the scale of angstroms. That's a 10 billionth of a meter. The waves of visible light are thousands of times wider than a single atom, on the scale of hundreds of nanometers. They're the beach ball to the atomic pebble. So a standard light microscope, no matter how powerful, will simply never see an individual atom. The light waves it uses are just too big. For centuries, the atom was a mystery to scientists. We knew matter was made of something fundamental, but actually seeing an atom seemed like pure fantasy. We were blind to the very building blocks of our own existence. We needed a new kind of light, with a wavelength small enough to actually touch an atom. And that breakthrough came from somewhere nobody expected. Our story kicks off in 1895 in a dark lab in Würzburg, Germany. A physicist named Wilhelm Röntgen was playing around with a cathode ray tube, which at the time was pretty high-tech stuff. Röntgen had covered the tube in black cardboard, blocking all the visible light. But he noticed a screen covered in a fluorescent coating that was about 9 feet away started to glow whenever he turned the tube on. Something Röntgen couldn't see was coming from the tube, sailing right through the cardboard and hitting the screen. He had no idea what it was. Röntgen thought he was going mad. He held up a book in front of the fluorescent plate only to see the outline of a key he had used as a bookmark. When he held up a metal object in front of the plate, Röntgen was able to see the bones in his hand. It was only when Röntgen invited his wife into the lab and showed her the bones in her own hand, and after she freaked out thinking it was an omen of her own death, that he accepted he wasn't actually going insane, and that he discovered a new type of light. Röntgen gave this new light a fittingly mysterious name: X-rays. Röntgen quickly found that these X-rays could pass through paper, wood, and even flesh, but were stopped by dense stuff like bone and metal. Röntgen took the world's first X-ray image, a haunting picture of the bones inside his wife's hand, her wedding band floating in place. The world was hooked almost instantly. For the first time, we could see inside the human body without making a single cut. But that was only the beginning. The real power of X-rays was still a secret. Scientists figured they were probably a form of light with a super short wavelength, but it took another 17 years for the next piece of the puzzle to click into place. In 1912, a German physicist named Max von Laue had an intriguing idea. He figured if X-rays are waves, and if atoms in a crystal are arranged in a regular repeating pattern, then maybe a crystal could act like a diffraction grating for X-rays. Now, a diffraction grating is just a surface with a bunch of finely spaced lines. When waves pass through, they bend and spread out and interfere with each other, creating a complex pattern, Think of it like a prism, but flat. Von Lau suspected that the tiny spaces between atoms in a crystal were just the right size to do the same thing to X-rays. He was right, and when his team fired X-rays at a crystal of zinc sulfide, well, they got kind of a blobby-looking result. But with a bit of refinement, they saw a beautiful pattern of spots. A pattern made of pure information. This was the eureka moment, but it took a father and son duo in the UK, William Henry Bragg and his son Lawrence Bragg, to figure out what it all meant. Lawrence, who was only 22 at the time, came up with a simple but brilliant equation, Bragg's law. It explained the relationship between the wavelength of the X-ray, the distance between planes of atoms, and the angles of the diffracted X-rays. This was revolutionary. The pattern wasn't random, it was a direct message from the crystal's internal atomic structure. By measuring the spots, their location, shape, and intensity, you could work backwards and calculate the three-dimensional arrangement of the atoms that made the pattern. It was a secret key to the invisible architecture of matter. For this discovery, the Braggs shared the Nobel Prize in Physics in 1915, making Lawrence Bragg the youngest person to ever win the prize in physics, and a new science was born: X-ray crystallography. So how do scientists today use this century-old idea to design new gadgets and life-saving drugs? The process is a lot more sophisticated now, but the basic idea is the same. It's a sort of three-act play: crystallization, diffraction, and computation. First, you need a crystal. Shocker that something called crystallography needs a crystal. X-ray crystallography needs things to be crystalline, where all the atoms or molecules are locked in an ordered, repeating 3D pattern. Think of a wall of brick, where every brick is identical and placed in the same way. This repetition is everything. Why? Because a single atom is way too tiny to scatter enough X-rays to be detected. It's like trying to hear one person whisper in a hurricane. But a crystal is a massive amplifier. Inside, you have billions upon billions of atoms all lined up. When the X-ray beam hits, every single one of them scatters the X-rays in the same way. All their tiny whispers add up, reinforcing each other, until they're loud enough for our detectors to hear. This is why getting a good crystal is often the hardest part, especially for biologists. They can spend months, even years, trying to convince a complex, floppy protein molecule to line up just right to form a crystal. There are some techniques that don't require a single perfect crystal, but these techniques aren't able to give the precise molecular structure and are more suited for looking at things like the purity of a sample. Once you have your crystal, which is often no bigger than a grain of salt, it's time for Act 2, diffraction. The crystal goes into an instrument called a diffractometer, where it gets zapped by a thin, powerful beam of X-rays. And these aren't the same X-rays you'll see at a doctor's office. X-rays for diffraction are often made in enormous city block-sized facilities called synchrotrons, a type of particle accelerator that slings electrons around a huge ring at nearly the speed of light. As giant magnets steer the electrons, they throw off incredibly intense and focused beams of X-rays. To understand how the atoms in a crystal interact with these X-rays, think of it like this. You're standing by a calm pond that has a grid of posts sticking out of the water. If you threw a handful of pebbles into the water, the ripples would spread out, bounce off the posts, and interfere with each other. Now imagine these posts are invisible, so you don't know where they are. All you'd see is a complex pattern of overlapping ripples. But a clever mathematician could look at that pattern and figure out the exact spacing of the posts that made it. That's more or less what's happening in X-ray crystallography. The X-rays are the ripples, the atoms in the crystal are the posts, and a detector acts as an observer. As X-rays hit the crystal, they're scattered by the clouds of electrons around each atom. These scattered waves interfere with each other. Where the waves' crests line up, they get stronger, creating a bright spot. Where the crest meets a trough, they cancel out, leaving darkness. The result, captured by the detector, is the diffraction pattern, a unique fingerprint of the crystal written in a language of spots. It contains all the information to determine the structure of atoms in a crystal, but it needs to be translated. This brings us to the final act, computation. The diffraction pattern gives us the position and intensity of the spots, but to build a 3D model, you need one more piece of the puzzle, the phase, which has to do with the timing of the waves. Today, we make computers equipped with sophisticated algorithms do the heavy lifting to determine the phases. And once the phases are figured out, the computer performs a kind of mathematical magic trick known as a Fourier transform, translating the pattern of spots into a map of electron density, a 3D contour map showing where electrons are clustered together. Since atoms are going to be surrounded by electrons, the peaks in the map show exactly where each atom is located. A scientist can then build a beautiful model, a digital sculpture of the basic unit of a crystal, and this unit cell, as it's called, can then be repeated to make the entire crystal structure. And while X-ray diffraction is the star of the show for crystals, it's not a solo act. Scientists have a whole toolkit. Techniques like X-ray absorption spectroscopy let them tune the X-ray energy to be absorbed by just one type of element in a complex material. This is ideal for figuring out what a specific atom is doing in a catalyst or a pollutant. Then there's small angle X-ray scattering, or SAX, which looks at bigger things like how giant polymer molecules are tangled up or the shape of nanoparticles suspended in a liquid. Together, these tools let scientists investigate matter on almost every scale. So what has this power to look at atoms actually done for us? The short answer is, well, the modern world. Probably the most famous discovery from X-ray crystallography is the structure of DNA. In 1952, Rosalind Franklin captured the critical X-ray image, the legendary Photo 51, which gave the twist away. DNA had to be a double helix. That one image allowed James Watson and Francis Crick to build their iconic model, unlocking the secret to life, heredity, and evolution. It's the foundation of all modern genetics and biochemistry. That legacy is going strong today, especially in medicine. To fight viruses, scientists can use crystallography to get a 3D picture of a virus's key proteins. This lets them see the exact shape of the active sites, the molecular machinery that it uses to copy itself, within the virus. With that atomic blueprint, chemists can design a custom-fit drug molecule that acts like a key jammed in a lock, gumming up the works and stopping the virus. In materials science, the impact is just as big. A material's strength, how it conducts electricity, or how it handles heat is all dictated by how its atoms are arranged. By using X-ray diffraction, scientists can understand why a steel alloy is so tough, or how a semiconductor transports electrons. This lets them engineer new materials from the atoms up. They can design lighter and stronger alloys for improved fuel efficiency. They can build better batteries to power our lives and store green energy. They can create new ceramics that are able to withstand extreme temperatures. The list goes on. Geologists use it to identify minerals, helping them piece together our planet's history. Environmental scientists use it to study pollutants in soil and water to find effective ways to remove them. Even art historians use X-rays to analyze the pigments in old paintings for conservation. From the texture of chocolate to the strength of a bridge, this technology has quietly shaped our entire world. From a strange glow in a dark lab to machines that let us look at every material under the sun, X-ray science has given us a new way of seeing. It has revealed the hidden blueprint of our world, from the DNA that defines us to the materials that build our civilization. We've learned to harness this invisible light not just to see the impossible, but to understand it and ultimately shape it. The atomic world is no longer just a concept. It's a landscape we can explore, map, and engineer. And the discoveries we're making there will continue to redefine what's possible. Thanks for watching. I actually have a fair bit of experience with a whole host of X-ray based techniques, including X-ray diffraction. I've also been to a few synchrotrons before, not to do crystallography, but still using the extremely powerful X-rays produced at these facilities. And I want to know, do any of you have experience with X-ray based techniques? Or maybe you're familiar with a different type of technique altogether and want to show it some love. Leave a comment and let me know. And if you want more stories about the science that shapes our lives, make sure to subscribe for more videos.